Okay, so let's read off a few more points about these model hierarchies that we've been discussing. And we said elegance and elaboration and how they have to meet somewhere. So, what happened here? Uh, so that's section 5 of this paper says elegance then and now. Make everything as simple as possible, but not simpler, said Albert Einstein, which is a paraphrase of what he said, but whatever he said, how can you ignore someone like Albert Einstein, right? So, a remedy for some of these issues was articulated by Isaac Held, who stressed the need for a hierarchy of elegant models, each of which contains no inessential complexity relative to the problem at hand. Schematically, this can be accomplished by starting at the bottom of each axis in equation 1 that we looked at, and for the processes of interest, selecting the first level at which those processes can be reasonably expected to emerge. So you ensure that the minimalistic elegance or maximum elegance with minimum complexity arises. So you start at the bottom and then keep adding something above that only if necessary, and only at one of those as necessary. Okay, if that doesn't make sense, don't worry, because this depends very much on knowing how to simplify the system. Most students may often end up using simplified version set up by somebody else already. So Isaac Held argued that elegance is necessary for progress in climate science, as inessential complexity obstructs understanding, hinders comparison with other studies of the same phenomena. So that's called the Babel effect that we looked at in the context of the cartography, and discourages adoption by other researchers who disagree with the inessential elaboration. Actually, the Babel effect should be the other one, not I'm just being a little thick here. So this is the on inexactitude in science, and this is come, let's go down and there confuse their language that they may not understand one another's speech. That's the babble here. So I don't know if that helps you or not, but nonetheless, just wanted to show you that. Of course, by defining elegance in terms of reasonable expectations and essential complexity, we are introducing significant subjectivity. That's what I meant by saying if you know how to reach reasonable elegance or reasonable expectation in terms of elegance and essential elements in terms of complexity, then you are probably already a expert in model hierarchies. Who is to say whether a given configuration is elegant? There must be this must be determined over time, as a given configuration is or is not widely adopted to study certain phenomenon. The fact is, when, let's say, Henry Stommel did the Western boundary intensification, he wasn't trying to be elegant. He was just trying to answer one particular question: why is there Western boundary intensification in the oceans? Or when Isaac Held worked with, I think, Arthur Howe and Held paper, I think it's held in how on the Hadley circulation. So there are historical examples of how people have created models that you look back in time and say, wow, that's really elegant. But can you really sit down and do it every time? Not always. The elegant models by definition must appeal broadly and be worthy of study in their own right, despite their idealizations. As such, they provide lasting value by furnishing common objects of study for researchers whose collective efforts are often stymied by modeler's conundrum described above. You can go back and read exactly what examples are used to define the conundrum, but we looked at the GFDL precipitation one. By the above definition, then a model's elegance is emergent. It's not something you start with, but once you set up the model and you show the process or the study, then you look back at it and say, wow, that's elegant, right? Beyond the quasi-geostrophic configuration of Phillips 1956, another configuration that seems to have emerged as elegant is the Held-Suarez configuration. So I mentioned Held and Howe, but this one, which solves the full rather than quasi-geostrophic primitive equations over a rotating sphere with no topography, ocean or ice, and with idealized surface drag and radiative cooling. So many assumptions are made to extract something, and this configuration, which might be considered the fruit fly of climate models, has been used with some modifications to study eddy mean flow interactions, extratropical temperature profiles, and stratospheric forcing of the tropospheric jet, among other topics. So it's a model that's set up with which with minimum modification gets you the essential complexity with elegance, but this is known after the fact. Here the fruit fly of climate model basically means that fruit fly often serves as the best way to understand genetics of human beings, because it comes pretty close. So many of the I don't know what's the best example. If you want to study something about the genetics of human beings and you cannot directly experiment with human beings, then you go back to the fruit fly and do experiments and so on, knock off a gene or add something and see what happens. Why does this gap exist? One answer is that bridging the gap would require elegant parameterizations for convection, cloud microphysics, and cloud macrophysics or cloud fraction, each of which seems to lack canonical first order approximations analogous to the diffusive boundary layer and gray radiation schemes employed in Frierson, the first convection model we looked at in Isaac Held's paper. A focused effort on such approximations, perhaps building on earlier efforts such as Molteni, will be needed to construct an elegant cloudy model and thus more fully realize the version of Isaac Held that we looked at. Well, these are all specific to this paper and the papers referred to here, like Molteni, which you will have to read to understand what exactly is being said. But generically or generally speaking, you know that there are certain processes which are complicated, maybe indispensable, and yet they are complicated, like convection, cloud micro and macrophysics, and they have no equation, so you're always ending up parameterizing them. So how do you keep elegance and head towards complexity, or keep maximum elegance and minimum complexity? That's how you would think about it. Perhaps progress lies in such a direction of our energies away from inessential complexity and towards elegance. Our scientific understanding is necessarily hierarchical, but unless our hierarchies are elegant, we will have difficulty understanding what our models are doing or relating their results to each other. Elegant structures should also help with comprehensive model development by helping us isolate complexity where we want it and eliminate it where we do not. Comprehensive model development must continue, of course, so that we may bridge the gap between our models and the real Earth, but a parallel effort in cultivating elegance also seems to be required to keep Babel and Borges in the distance and so ensure that our model hierarchies provide the understanding that progress requires. It all sounds a bit philosophical, but it is supposed to be so, because after all, elegance is still very subjective and descriptive term in many ways, and it's an emergent property, let's say. Complexity is always essential, but how do you decide what's essential and what's not? That is often subjective, but once it succeeds, like in the examples of the models we mentioned, and everybody looks at it and says, wow, that's elegant, and especially if it can be used for multiple problems, like the eddy mean flow interactions, then you have obviously created an elegant model. I'm going to leave it there anyways. This is a good part of the modeling course. Maybe I won't put it in new findings under climate change So if you read it here and hear words about new findings, then just ignore the words. Okay, see you next time.